Okay, we're going to have a review of some of the 2020 Paper 1 A-Level Computer Science questions. This is just a sample, and I'll try and timestamp this so we can jump to those individual topics. We're going to start off with binary, hexadecimal, and floating point questions. With one of them with a bit of a twist that could easily throw you, so it'll be good to go through these. First of all, we have this question with a negative denary number. Hopefully we're immediately thinking there's two ways we could represent that in binary, either with sign and magnitude or 2's complement. In this case it's 2's complement, in which case the most significant bit will be negative 128 in a 8-bit number, as opposed to sign's complement where it will be positive or negative. So if you remember, the recipe is make a 119 positive, flip all the bits and add 1. So let's try and do that. Okay, and I've got my number I want to make. I want to make the positive version of it, so positive 119. If the number was bigger than 128, could you do it? So say if it was negative 129, could you make that number? What's the largest negative number I can make in 2's complement with an 8-bit number? Exactly, right? So I'll make 119, so we'll go across, put the ones where we need them to be. Next step of the recipe is to flip all the bits, and then finally we need to add 1 to the least significant bit. In this case it will be adding 1 to the value here, giving us the value in the end in 2's complement of, bear in mind if that was a 1 we'd have to carry it across, and if there was a series of 1s then we'd have to do quite a lot of carrying. Alright, brilliant. Convert the unsigned binary number to hexadecimal. So this is the question that might throw us a bit, because, well, why do we have hexadecimal? We have hexadecimal to facilitate the communication of binary between people, because each hexadecimal digit is represented by exactly 4 binary bits, and in here we have a number which has 7 binary bits, which is not normally what happens. What normally happens is that we have 8, 12, some multiple of 4. And the question is, what do you do here? Well, we start from the right and we still split it into lots of 4. And then the one on the left, well, you could either pad with a 0 there or just consider it blank, which is effectively the same as 0 in this case. And we want to convert it to hexadecimal, so remember that would be an 8, a 4, and a 1, so that would be 13. Do we write down 13 in hexadecimal? So we'd write down, if A is 10, B is 11, C is 12, therefore we'd write down D. And on the other side, this would be a 1, that would be a 2, that would be 4, so we'd say for 6D. Normally, the curveball they throw you for a question like this is they'll ask you like a 12-bit number or a 20-bit number, and you just break it into a series of 4. I've not seen this sort of particular version being done before. If I did it by counting 4s from the left-hand side, would I get the same result? No. So you do it from the right. Convert the denary number 171 to hexadecimal. So I've got 171. If I want to convert into hexadecimal, what will I have to do? So you could convert it to binary and then break it into nibbles and convert them individually. Could do that. Could also ask the question, how many, because remember it's going to be lots of 16s and then lots of 1s. The question could be, how many 16s can you fit into 171? In some ways it's quite a kind question. How many 16s go into 171? 10 16s is 160. 11 16s would be 176, too far, so it would be 10 16s, and then 171 take away 160 gives you 11. So you've got 10 and 11. However, we'd write it down as 10 and 11. No, we'd write it down as A, B. Alternatively, if you wanted to convert it to binary and then turn that into hexadecimal, yeah, it's also completely fine. Obviously do it as a byte. And then finally convert A6 to binary. So we started with our A and we got our 6. Each of these is a nibble. So we can do the left and right side nibble. 1, 2, 4, and 8. 1, 2, 4, and 8. A in hexadecimal is the value 10. So that would be a 1 and a 0 and a 1 and a 0 and 6. Well, that's just a 6. Alternatively, if you can't remember how to do that, you could say A times by 16. So 10 lots of 16 is 160 plus 6, 166. And you could convert that to binary, by going through the whole grid of numbers. Okay, and now we've got a bit of a jump up. It's a kind of normalized question, which are normally worth a few points for us here. Show how the denary value negative 9.125 can be represented in normalized floating point, normalized point format. If you remember, that was normalized. If it was a negative number, it would be negative 1.0 something, and if it was positive, it would be 0.1 something. So the first part of the recipe is to put it into fixed point, absolutely. So let's make sure we do that on both sides. So we've got fixed point version of this number. So go 1, 2, 4. Do I have enough? No, I'm trying to make 9. Do I have yet enough? Yes, I do, but only positive 9. So I'd have to make negative 16 over here. And on the other side, what is 0.125 as a fraction? Well, it is 1/8, isn't it, in this case? Yeah, but yeah, I appreciate what you say. We're going to have to flip it. And actually, this is not that dissimilar to the last question because we've got negative 9.125. Now, your choice is either make positive 9.125, flip and add 1, or you could just make negative 19 directly. Which do you feel more comfortable to do, guys? Thank you for the feedback. As always, this makes me feel... So you could do it directly. You could say, maybe I'll talk it through both ways, but maybe I'll show you the flip one because you might find it a struggle. And maybe I will actually, to be honest, this morning. We'll find out. Negative 16 plus 4. Well, negative 16 plus 8 is going to be too far because that will give you negative 8. Negative 16 plus 4 is going to give you negative 12. Plus 2 is going to give you negative 10. So I'm almost there. Plus a half, a quarter, and an eighth is 7/8. So that will get you negative 9.125. Or alternatively, maybe I'll show it for, because maybe you get a more complicated question you want to make. You can do the same as we did previously in the sense that you can make the positive version. So this is positive 9.125. And then you can flip them all. I think the one place that you can have a struggle sometimes is then when you add a 1, you add 1 to the least significant bit. So don't add a 1 here. Add a 1 here in the least significant bit. And then you get the value of 10110.111, which I believe is what we just said. So, negative 6 plus 4 is negative 12 plus 2, negative 10, plus 0.75, next negative 1.25. All right, first part of the recipe done. We've made the value in fixed point. Then we're normalizing it. Now, as a reminder, normalized, if it's positive, it's 0.1 something. Negative, it's 1.0 something. Positive, negative. And the number, to state the obvious, is negative. So we have to float this point to make it 1.0 something. Please don't float it this way, because then you will delete all of that data. That's not so smart. Where do I need to move? Once, twice, 3 times, 4 times to the left. Let me write that out. 1.0 110.111. Okay, now do you remember there's this relationship between the mantissa and the exponent? When the mantissa becomes smaller, what has to happen to the exponent? Becomes larger. And if the mantissa becomes smaller, then the exponent becomes, and if mantissa becomes larger, the exponent becomes smaller. Has the mantissa become bigger or smaller? And remember, if you're sat in there thinking, I can't quite figure it out, just do it with denary. 14.6, whoops, why have I changed the color? 145.6. If I move this point this way to make 1.456, have I made it bigger or smaller? If I move the point to the left, have I made it bigger or smaller here? Smaller. Yeah, it's consistent with the same way. If the mantissa becomes smaller, what has to happen to the exponent? Becomes bigger. How many times do we move it to the left? 4. So the exponent is now 4, and it's a 4-bit exponent, is it not? So we'd have to say it's times 2 to the 0, 1, 0, 0. Question, is the exponent also in 2's complement? Has to be, right? Otherwise you couldn't do smaller numbers. Have I finished? Is it good like this? What do I need to do? Well, the mantissa is how many bits? The mantissa is how many bits? 8. I've currently got, maybe I'm okay. 1, 2, 3, 4, 5, 6, 7, 8. Oh, beautiful. Okay, actually is okay. Do you record the point inside the computer? No, because the point is always between the first two if it's normalized. So I'd say 1, 0, 1, 1, 0, 1, 1, 1, and the exponent is... Point means that the computer knows that the point is there, and it also knows it's an 8-bit mantissa and 4-bit exponent. Okay, quick question on masks. If you remember, there are 3 types of masks that we can apply to a series of binary bits to allow us to do different functions. Could allow us to reset values, or clear values, or toggle values. What are the 3 different masks? We've got an AND mask. We've got a OR mask. And then, like in this case, we've got a XOR or XOR mask. Just as a quick reminder, and, so obviously each of these could either be a 0 or a 1 for all of them. Let's go through it. If I apply an AND, so there's 2 inputs going to an AND gate. If one of the inputs is 0, what would the output always be? 0. So this allows us to clear anything where I put a 0. If I put a 1, it stays the same, so it keeps the original value. With an OR, anywhere I put a 0, well, it won't change what the other one is. If the other one is a 0, it will be a 0. If there was a 1, it would be a 1. Anywhere I put a 1, if one of the input is 1 on an OR gate, what will happen? It will turn it on. So this is when you want to just switch things on, basically. And a XOR, if it's a 1 or a 0, and the other one is a 0, it'll stay the same, right? But if it's a 1, if it is a 1, it will make it 0. If it's a 0, it will make it a 1. It toggles, exactly. So reset or clear, turn on, toggles. In this case, what we got? Here we go. Show the results of applying an XOR mask. So working from right to left. Remember, exclusive OR, the only difference between that and an OR gate, in an OR gate, if they're both 1, the output is 1. But with an XOR, if they're both 1, the output is a 0. In fact, maybe I'll just do that quick little truth table. XOR 0, 0, 0, 1, 1, 0, 1, 1. And then in terms of outputs, if it's a 0, 0, output 0, 0, 1, 1, 1, 0, 1, and then 0. Cool. Well, then let's go through and try and fill out all this bit here. And as you can see in the result here, everywhere where the XOR was a 1, it toggled what it was. So originally it was a 1, it became a 0. Originally it was 0, it became a 1. Anywhere where you put 0, it kept the original value. So this is just the same as it was originally. And then at the end, yeah, another couple of times where it toggles. And now it's asking you to think about another mask you could use that could be applied to an 8-bit number to ensure the most significant bit is always set to 1. Which side is the most significant bit? On the left. And all the other remains to change. So what do we do that enables things to always be 1? Which one are we going to use? An AND switches things off. Yeah, an OR, if the input for an OR gate is 1, it will be on. So I would say an OR gate or an OR mask, and then what's it going to look like? What's the most significant bit is always 1, and the rest are always unchanged. So what's it going to look like? With an OR gate, the 1 in the most significant bit will be, no matter what the original is, will be 1, and then the 0 means it will be kept the same. And like I said, the other combination you can have is a question which said, for instance, the most significant bit needs to always be 0, and the rest is the same. In which case, I will do an AND mask with the most significant bit being 0 and the rest being 1. Cool. Okay, and now we're in the midst of ways of simplifying logical expressions. If you remember, there were 2 techniques we learned to use. One was called Karnaugh maps, and the other one was using simplifying Boolean expressions by using Boolean algebra. I think Karnaugh maps are a bit more of a practically straightforward reason for us, but of course you won't get to choice in the real thing. You'll have to do whatever's made available to you. In this case, it's a Karnaugh map, a 4-variable Karnaugh map, and we're given the expression here. This one here, this symbol here is a not. That's the upside down V is a and then that is all the expressions are linked together with these ors. So let's take it one at a time. In fact, I will highlight that bit in blue. Oof. And then the other one I'll highlight in red. So we're looking for places where not A, so where A is 0. So A is 0 here and here. So if it was just not A, it would be all these values here. However, there's also not B. So where it's not A and not B. So we need to look for somewhere where A and B are both 0. In that case, it will be, well, if you look, the only place where A and B are 0 would be on this column. So I can type it in here. And then I need to do the same with the other expression. A and not B. So because it says A, it's where A is 1, and not B, where B is 0. So that's the first start, is that we've now filled in the Karnaugh map. That's quite generous, really. They gave you 3 marks just to do that. And now they're saying, can we use the Karnaugh map as a tool to simplify the Boolean expression? Now, if you remember, the rules of the games are this. You want to, you have to draw boxes around every one, but the boxes should be as large as possible. You should use as few boxes as possible, and you can fold. So one of the things you might do, for instance, let's say, is if you drew a box around this one and a box around this one, what have I just done? If I simplify that, what do you reckon I've just done? Yeah, exactly. No change whatsoever. So that's not exactly the smartest move I've ever made. The big trick where they're trying to, I don't know if they're going to catch you out, but you have to make use of for this one here, is that they're asking you to fold. So this can fold across to the other side. Yes? And because you can fold off from both sides, that's going to allow us to simplify. And remember, what we're looking for when we do this is, what are the variables that do not change? So anything that changes, so you can see C is 0 here and 1 here, it cannot be that value. D changes. A is 0 over here and 1 over there, so that changes. But what stays the same is you've got not B over here and not B over here. So in the end, the actual answer would be not B. Okay, and now we're looking at circuits that you can form with the gates that we have. The most common circuit that comes up, what is the most common circuit that's going to come up? Yes? The half adder, right? Okay, and conceivably you could be asked to draw a half adder. Maybe while we're here, maybe it's worth just remembering. Remember, we talked about a tool to allow us to draw a half adder. What you did is that you got the inputs A, B, and what the sum is. So we can have all the different inputs for A and B. So we're adding these numbers together. If we add A and B, so this is not D-type flip-flops, this is half adders. I'm just taking the opportunity while we're doing circuits, because I think this is actually the more common one. If I add A and B together in binary, what does that give me at the end? 0, so the sum would be 0. 0 and 1 will give me 1. 1 and 0 will give me 1. But with this one, with 1 and 1, how do you deal with adding 1 and 1 together in binary arithmetic? You carry the 1. So I need an additional column, carry. And for this one here, the result was 0, but the carry was 1. What's the carry for the rest of them? 0. So this is just a tool I'd have for yourself. Now what you want to do is you want to evaluate this as inputs for a truth table, and that as the outcome. What gate has these as inputs and that as an outcome? Yeah, that's right, XOR. We've got our XOR gate here, and the inputs are A and B. These will be inputs going into this gate. And then the other one what is the gate where you have A and B, and this would be the outcome. It would be an AND gate, which I kind of have a spoiler going on there. Oh, question. Would it be smart for me to do this, in terms of drawing the logical circuit for a half adder, to do A and B and then connect them like so? Would that be smart? It wouldn't. There is only one A and B, and what I have to do is I'll connect it up like so. I can't even make it touch. Come on, there you go. And then the B will come down and be connected. Got lost in my hairline. Excellent. What's next? What's the outcome? What's the outcome for this? S. And the other one? C. Limitation of half adder? Yeah, it can only add in a single A and B, so it can only do 1 bit arithmetic, because for the next one, you'd have to take in a carry as the input, and this can only take 2 inputs going in here. So what you'd have to do is you'd have to connect this carry into the next adder by, instead of having a half adder, having a full adder. And if you're, I don't think you'd have to draw it. Well, that question's never come up. I mean, conceivably you could, but I don't think so. But you might have to recognize it. And basically, a half adder looks like, sorry, a full adder looks like a half adder. The only difference is that the 2 carries that you put together go into an OR as an output. So it's basically, a half adder has got 2 lots of these, and then it goes into a OR with the 2 carries. Anyway, let's go back to the actual one we did. D-type flip-flop, never seen you required to actually draw a D-type flip-flop or even recognize it, but you do need to know how they work. What's the purpose of a D-type flip-flop? What are they actually trying to do? So a half adder is trying to add a number together. This is as basic as that. So your computer needs to add things. What else do you reckon it needs to do? It needs to store things, right? You need to store values, don't you, in a computer? And a flip-flop is the primary component to be able to store a value. How many values is a flip-flop going to store? It's not what you call an impressive amount of storage. What's the smallest thing that you could have in a computer? Huh? No, a single 1 or 0, a single bit. So a D-type flip-flop can store a single 1 or 0. Do you know what the D, when it says D-type, what do you reckon the D stands for? Oh, sorry. So it stands for dynamic, and the way it works is that you've got a clock input, and then you've got a secondary input, which is sort of like the data coming in, whether that's 1 or 0. And you're quite right that on the clock input, that when you have a clock impulse, like so. Wow. Okay, I'll try that again. So with a D-type flip-flop, one of the inputs will be a clock, and essentially the clock is something like this, where you've got impulses going along, and the rising edge, which is this one here, the idea is that values only change on the rising edge so that it's in sync. So one of the inputs will be the clock, the other one will be the actual data itself, and what will happen is at the rising edge, or when the rising edge happens, it will check the value of D, and if that is, or the data input, if that is 1, then the value stored will now either change to 1 or still be 1, and or if it's changed to 0, it will be that. If the value changes between, is in the input that comes in changes between a clock cycle, nothing happens. Values are only updated when the rising edge happens. So what is the purpose? Well, what did I say it was trying to achieve? Stores a value, in this case a single bit. And then I think this is the final topic people asked to have a look at, which was little man computing. Please indulge me for a second while I try to put this in context again. So this is, what kind of language is little man computing representing? Assembly languages. So languages, remember, go on a So this comes up in multiple things. So we learned about programming paradigms, about procedural programming languages, object-oriented programming languages, decorative languages, and assembly languages. So that was one of the paradigms of how you can write code. It also comes up in high-level languages versus low-level languages. So a low-level language is closer to the machine level, and then they all need to go on some journey when you start with human-readable source code and end up becoming machine code. And in assembly languages, the conversion is an assembler, straightforward one-to-one conversion of essentially an instruction with an opcode and operand into the machine code version of it, as opposed to a high-level language like an interpreted language or a compiled language where you have to go on a different translation journey with a compiler and interpreter. And we essentially just need to be able to write code in low-level machine code using, low-level language like this for assembly. I suppose the other place it could come up is in terms of types of processors. What type of computing is little man computing in terms of processor? Like how many instructions do we have? Yeah, not very many. Is it RISC or is it CISC? Good question. RISC. So it's also reduced instruction set computing. So like little man computing can be like a little tool that could be used and come up to describe multiple different areas, I guess is what I'm saying. And yeah, it's definitely RISC in the sense that it's not covering any things. And how many addressing modes do you remember little man computing has? What do I mean by addressing modes? So addressing modes were when you have an operand, what is that value? Is it the value directly? Is it an address where I can find a value? Is it an address where I can find another address where I find the value? Right, so there was like immediate addressing when the operand is the value itself, direct addressing when the value in the operand is an address where you can find the value, and indirect addressing is an address where you can find another address where you can then find the value, and there's also index linked addressing where you've got an index register and it's an offset. Do you remember what little man computing does? What kind of addressing? So it's direct addressing. So if you wanted to have the value 1 and reduce it, you actually had to have a memory location with the value 1 and use that to take a value off. You can't have, and that's quite classic of RISC processors, not guaranteed, but CISC processors generally have multiple addressing modes, while RISC only really has limited. Of course, a lot of computing these days is done on RISC, so that's evolved a lot, but once upon a time it was classic that there was limited addressing modes. Anyway, we've got the mnemonic, the opcode, and then we've got the instruction. STA, do you remember? Stores the value, so it stores the value of the value held in the which register? Gosh, yeah, and you could also do registers through little man computing. That's classic, okay? What value, which register is it going to move to where to where? Yeah, stores value from the accumulator to address indicated by operand. So totally, I know, but I'm trying to like do a 7 for 1. So if it said STA4, it would store the value in the accumulator at address location 4. I'm sure you're right. I'm sure they do just want you to write store, but you know this could come up in so many different contexts, and I'm trying to do it. Branch always. So that says based on the value held in the accumulator, whatever that value is, jump branch to the section of code that you indicated. So do you remember what the code for this is? BRA, and then BRZ. It's branch, right? But branch under what conditions? Yeah, branch if what is 0? Absolutely. If value in the accumulator is 0. BRP. If what is positive? Yeah. I think, truthfully, this is a very kind question. I don't think you get a question like this come up. I could be wrong. But it's still nice to do. Helps us do in here. Final one. We don't really... Do you know, truthfully, when we write a code, we very rarely actually wrote this down. Do you remember what it is? Yeah, HLT, because it's mnemonic. But yeah, halt. And basically it just means when you get to this line, finish. Truthfully, if you didn't put that down, it runs out of instructions. It also stops. So, all right, cool. So we've got 5 marks. And then the next bit is write a program using the little man computer instruction set that will allow a user to input 2 numbers and then output the larger of these 2 numbers. And then the question is going to be is, do you want to use things like DAT to store that number? Do you remember we used DAT as a command where you could actually store the name of a number? So I might use that because it reserves a memory location for us. So I'll say at the bottom, right at the bottom, because I might run out of space, num1 and num2, and then the code DAT. What that will do is it will reserve some memory location, well, at the end of your instructions, because it's, oh, there you go, another teachable moment. Little Man Computing uses von Neumann architecture. What's one of the things about von Neumann architecture? Instructions, yeah. Both data and instructions are stored in the same place. Remember, we got to demonstrate it a long time ago where you can actually override an instruction with data and then break your code, which is obviously not super smart. When you do DAT, it ensures that when it puts it into memory, the memory locations restored for num1 and num2 are after the instructions, so that you don't write over it. Okay, we got x1, x2. Okay, so this will reserve 2 memory locations for num1, num2. What else do we need to do? So what's the first thing? It says allow user to input 2 numbers. So I'm going to, I mean, you can say what you see. On the left-hand side, it says, it literally says the word input. Should we do that? Let's do that. Good choice. IMP, so it's going to input the value. When I get it inputted, what should I do with this value? Store. So STA, and then what? Now? Yes, input again. And then, well, it's essentially just what we just did. Although technically, no, technically you don't need to actually store this one, do you? Because it's in the accumulator. Oh no, that's not true, because you need to sub it, and then when it subs it, you won't have the value in the. Yeah, so we do need to actually. I change my mind. Because how are we going to describe? Because it's the higher of the two, isn't it? It says. How do we decide whether one is bigger than the other? In the accumulator right now is the value for num2. If I take away num1 and it's positive, what does that tell you? So why don't we say sub num1. So we have num2 in the accumulator. We took away num1. And then what command we use? We use brp. And that would indicate what? Okay, branch. So how about I say second or something? Do you remember how we can then jump to some place? Well, on the side here, you'd have to say something. So I could say here, I could say second. I'm going to run out of space here. If I said, so this is being a bit lazy. Well, not lazy, I'm maybe efficient. I'll say if what's in here is positive, then it indicates that the second number is larger. So therefore, what should I do? Load LDA? Yeah. Load num2. Oh, I'm going to really, and then output it. Output. If it wasn't larger, then what happens? Load number 1. This is where I've kind of screwed it a bit because I need another spot here, don't I? Imagine that this was underneath the next thing I write down. Out. Okay. I've not got all the marks. What have I missed out? Which I'm, huh? Yeah. So how am I going to make it loop? So how about okay, how about I write something like loop? Yeah? That's imaginative, I know. Say what you see. For which one?
Like before, like last end, like end, for example.
Like here?
Yeah.
Yeah. I can say, what should I put in it? Yeah, sounds good to me. BRA loop. Question. Is there any problems with my code? Huh? Yes. So the way it's going to work is it's going to say, aha, Yes, second one wasn't the larger one, so therefore the number one gets loaded and it's outputting it. And then what will it do? It will do that, and then also load the second one and output it, and then restart. That's not the goal, is it, realistically? So what do we need to change? Yeah, we need to, after this output, what do we need to do? BRA and then loop. Basically, here where I gave myself one space, I actually needed 3 lines, which is not super smart, but what can you do? Happy?